All right, good morning, everyone. Can you hear me? All right, cool. Just checking. I'm using a different computer today. I actually had some issues with my last computer and lost the last two videos I recorded for your class. So I'm gonna have to re-record those videos and post them on YouTube. Um, but aside from that, this is my Tuesday, Thursday, 8:30 a.m. class, and we haven't talked about graph theory yet. So hopefully all of you have been watching my YouTube channel and saw the vague introduction to graph theory that I posted last week. In today's lecture, we're going to go into this in more detail, and this is going to slowly prepare us for the optional final project. So again, um, uh, today we are going to look at graph theory. Okay. Okay, so this topic is of particular interest to me. Wait a minute. New computer, I got to switch my screen around. Um, 1 second. See how it's backwards on the board? Where is it? One second. Um, everyone sees this, right? Like, is my text on the board backwards? Or am I the only one that's seeing that? It's good? Okay. So it's just me. So let me fix that for myself real fast. Okay. That was just for me. All right. So graph theory. So I'm a graph theorist. My PhD is in graph theory. So I like it. I've spent many years studying it. So I'm kind of excited to share it with you. Okay, so recall from my last YouTube video the definition of a graph. So a graph is um, a well, a graph consists of a non-empty vertex set typically denoted V of G. So a graph G consists of a non-empty vertex set V of G and a edge set E of G, where each element of E of G consists of two vertices in V of G. Okay, so this is the general definition of a graph. Okay, a graph is a pair of sets. It's a vertex set and it's an edge set. Okay, now let's look at like maybe an example. So let's say, so G is the graph. With, let's say, vertex set A, B, C, D, E, and edge set equal to, I don't know, say A, B, A, C, A, D, B, D, C, D, and C, E. Okay, so so this is a graph. It happens to be the case that we can represent graphs with drawings, right? And this helps us kind of understand the underlying relational structure defined by these two sets. So it doesn't matter how you draw them. Just kind of say maybe this is A, B, C, D, E. So those are the vertices of the graph, and there's an edge AB. There's an edge AC. There's an edge AD. There's an edge BD. There's an edge CD, and there's an edge CE. This is an E, by the way, if you can't see it in the glare. Okay. So that's a pictorial representation of this graph, right? So one thing that's important to remember about graphs is that this definition is a pair of sets. It's a vertex set and an edge set. This is just a drawing that represents the actual graph, right? And the drawings can vary. Like this is one way to draw it. Another way to draw this graph would be something like this. Right, this is the same graph as that. It's just drawn differently, right? Like this could be like E, this could be C, A, D, and this could be B. And this preserves the same relational aspects of these two sets. So a graph is really, it's a discrete object that describes relationships. So now there are several different types of graphs. And the different types of graphs are determined by how the edge set is defined. So let's go ahead and look at that. So, so the different types of graphs are determined by how E of G is defined. Okay, so how the elements in E of G, how the elements in the edge set are defined. So, so for example, so elements in E of G are any unordered pair of vertices. So this is just a general graph. If you can have any unordered pair of vertices as elements in there, that's a general graph. And then we can have elements in E of G are ordered pairs of vertices. These are what's called directed graphs. So if the elements in the edge set are ordered pairs, these are directed graphs. There's a beginning endpoint and an end endpoint. And then finally, if E of G is not directed, and contains no loops or multi-edges, and I'll explain what those are in a second. These are what's called simple graphs. Okay, so I think the best way to illustrate these different types of general graphs is to just draw them. So let's look at like a general graph here. So maybe E of G equals to A, B, C, and D. In E. And then maybe the edge set is defined as maybe AB, AB, BC, BD, EC, EE. So if those are the edges, so what does this look like? So there's A, B, C, D, and E. So there's an edge AB, there's another edge AB, there's an edge BC, there's an edge BD, there's an edge EC, and there's an edge EE. So just some terminology. The vertices that make up an edge that say vertices that make edge E are the endpoints of E. So every edge consists of at least two vertices, not necessarily distinct, and those are called the endpoints of the edge. Right, so this right here, this is a general graph. This is just the most general definition, general graph. Okay. All right, so let's look at a directed graph. So maybe V of G is equal to A, B, C, D, and E. And the edge set is defined as now ordered pairs for a directed graph. So maybe something like AB, AC, CB, CD, and then EA. So now the elements in the edge set are pairs, or ordered pairs, which means that there's a beginning and an end to each edge, or a head and a tail. All right, so those are my vertices. So there's an edge from A to B. There's an edge from A to C. There's an edge from C to B. There's an edge from C to D. And there's an edge from E to A. So this is a directed graph where each edge has a beginning and an end, or a head and a tail. Now, so this is a directed graph. Okay. So, okay. Now, what we're going to focus on in this class is we're going to focus on the last one here, simple graphs. Okay. So simple graphs are graphs that are not directed and they contain no loops or no multi-edges. So what is a loop? That's a loop. Edge E right there, I mean the edge right there from E to E, that's a loop. So, a loop is an edge whose endpoints are the same vertex. That's a loop. See that edge right there? E to E, E to E. So that's a loop. Okay, so simple graphs will not have loops. Right? No edge is going to go from itself back to itself. Or no vertex is going to be sent to itself by an edge. So multi-edges. So multi-edges are multiple edges with the same endpoints. Barely fit it on here. So multiple edges with the same endpoint. So here, so this right here, this edge EE, this is a loop. And then these edges here, these are multi-edges. Because they're edges with the same endpoints, AB and BA. AB and BA. And you can see that there's multiple edges between A and B right there. Okay. So simple graphs are graphs that do not contain multi-edges. All right, so if I were to get rid of this picture and draw a simple graph, it would not have So if I got rid of that edge right there and that edge right there, that would be a simple graph. But let's go ahead and just like draw another one. So if we do like AB, BC, AC, CD, and then AE, then if we draw this, there's going to be no, well, we don't even have to draw it. There are no multi-edges in here and there are no loops. So edge AB, BC, AC, CD, AE. So this is now a simple graph. Because there are no loops or multi-edges. Now, graphs have many applications. In simple graphs and directed graphs, they have different types of applications. So for example, Facebook would be a giant simple graph, where the Facebook accounts are the vertices in the graph, and there's edges between accounts that they're friends. Whereas something like Instagram would be a directed graph, where you can follow someone, but that doesn't necessarily mean that they follow you back. So there's a direction on the relation on following someone in Instagram, basically. So these types of relational structures can tell us a lot about, for example, how ideas or memes spread in a social network, or how maybe political influence spreads in a social network. They can also be used in various applications, such as like, for example, a lot of dating websites will create graphs based off of whether or not people are compatible, and then along the edge they'll put a weight to say about like how compatible they are. And the job of like the people programming these algorithms is to find the best match among the given collection of people on that website. Or, for example, like organ donors and people that need organs, right? There's a relational structure there. If they have the same blood type and they're a viable candidate, then these two people can be linked up by an edge. And then you can do that among all possible donors and receivers. And then your job is to match them up the best you can so that everyone, so you can optimally provide organs to people who need them. And we're going to actually do an algorithm that's very similar to that as the optional final project. And we're going to focus on simple graphs though. So directed graphs are good, but just know they exist. We're going to focus on simple graphs. Graphs without multi-edges and no loops. Yeah? Okay, so definition. All right, so I'm going to say let G be a simple graph. So I'm not going to write simple graph all the time. We're just going to assume that all graphs in question are simple. All right, so now we're going to get down some terminology that we need to study graphs. And all of the definitions I'm about to write down are very important. Please write them down. So two vertices say V and W that are in the vertex set are called neighbors or adjacent if there is an edge with endpoints V and W. So i.e. VW is in the edge set. Okay, so this is a very important definition. So neighbors or adjacent, these mean the same thing. Neighbors and adjacent mean the same thing. Okay, so I'm just going to draw a graph over here to the side. So here's some graph. The W, by the way, Q, V, X, Y, and Z. Okay, so let's continue this definition. The neighborhood, but it's technically called the open neighborhood, of some vertex V in the vertex set is the set of all neighbors of V. And this is typically written so this is the set of all W such that W is adjacent to V. Okay. So as an example, you can drop the subscript G when the graph in question, you know it, so you can write that as well. So for example here, the neighborhood of Q, so the neighborhood of Q is a collection of all vertices that are adjacent with Q. So well, who's adjacent to Q? Well, V is adjacent to Q, X is adjacent to Q, and Y is adjacent to Q. So that's the neighborhood of Q. It's a set of all vertices that are adjacent to that vertex. Right? Is that clear? Okay. Okay. The degree of some vertex V is, so degree of V, and that's just equal to the cardinality of the open neighborhood of V. The cardinality of the neighborhood. So here, the degree of W, so the open neighborhood of W consists of Y, V, X, and Z. So the degree is just the number of neighbors. So W has 4 neighbors, so the degree of W is 4. Okay. So again, these are all important definitions. All very fundamental definitions that you need to study more in-depth notions in a graph. A few more. So the order of G is typically denoted by n of G, and that's equal to the cardinality of the vertex set. Okay, so here the order is so 1, 2, 3, 4, 5, 6. So it's just the number of vertices in the graph. Okay, so if I ever say order, that's what I mean. The size of G is typically denoted by M of G, and that's equal to the cardinality of the edge set. So that's the size of the graph. Okay, so how many edges are here? So what is the size of this thing? If this is G, so 1, 2, 3, 4, 5, 6, 7, 8. I'm pretty sure there's 8 edges in there. So that'd be the size of the graph. Okay. So far, so good. Again, all of these are just definitions. And so I'm going to draw another graph. So I'm going to erase these definitions, though. We have neighbors and adjacent mean the same thing. Neighborhood, set of all neighbors of a vertex. Degree, the number of neighbors of a vertex. Order, the number of vertices in the graph. And size, the number of edges in the graph. Okay, so I'm going to draw several graphs here. So I'll call this graph G. And then I'll draw another graph over here. I'll call this graph H. Six. Okay. So some quick questions. So what is the order of G? You can answer in the chat, or you can say out loud. What's the order of G? Right, so we have 8 vertices, right? 1, 2, 3, 4, 5, 6, 7, 8. So by the way, plural vertices, a singular vertex. So if you say vertex C, it's not vertice C, it's vertex C. So what is the order of H? Again, it's just the number of vertices, right? So it'll be 7. Okay. So what's the neighborhood in the graph G of vertex E? So it's the neighborhood of vertex E in the graph G. So I call it a set. So we got F, H, D, G. Let's see if that's correct. So F, H, G, and D, yeah. Okay. All right, so, and then I guess like, what's the degree of vertex 1 here in this graph? Anybody? Three, right? Vertex 1 has 3 neighbors. Okay, look up the size. What's the size of graph H? So the size of graph, I mean, so it's not the vertex, the size of graph H is the number of edges. So it'll be 6. There's 6 edges. So that's, yeah, 6 edges. Okay. So typically, uppercase letters will denote sets and actual graphs, where lowercase letters and numbers will denote the vertices of a graph. Okay. Is there something different about that graph? Does it look kind of odd? Like, I guess let me just draw a bunch of graphs to see if you can catch what I'm talking about. So, like this is a graph. I'll call this like G1. This is a graph. I'll call this G2. This is a graph. Call it G3. And then draw another graph. Call it G4. I don't know. G5, maybe. G5. So what makes G1 different than the rest of these graphs? How is G1 different? Anybody? G1 is different fundamentally somehow than these other graphs. So there's a point that doesn't connect with more than one. Okay, so let me draw. So you're on the right track, but okay, still, I changed G1, but it's still fundamentally different than G2, G3, G4, or G5. There's something off about G1. It's not the same as these others. What's another way to draw this thing? Let's see if we can draw this a different way. So here's A, B, C, D, E, F, G, H, and I. So I'm going to draw this graph again. So here's A, B, C, and D. So, and then here is and then so here's like E, F, G, H, and I. So this is still G1. That's the same graph. If you look at the relationships, like D is related to C, D is related to C, D is related to A, D is related to B, it is. A is related to B. So all of the relations in this image are the same here. It's just a different way of drawing it. But doesn't it look different than the others? What makes it look different? Somebody. How is G1 different? It's like right in front of you, right? How are they different? Somebody's got to say something. How is G1 different than G2, G3, G4, G5? Anybody? I'm gonna wait. That is one graph. What do you notice about it? It's one graph, but something. Someone's got to give an answer here. And you don't have to say anything like, there's no, like, you don't have to be formal about it. So this is not a directed graph, though. Just look, there's two pieces. See, there's one kind of piece that's all together, and then here's another piece that's all together. This is one graph, but there's two pieces when you draw it. Like here, there's just one piece. 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 But here, there's two pieces when you draw it. Now that's interesting because graphs are just defined as sets, right? Like I really don't want to like list it all out, but this is a vertex set and an edge set, and you can draw it any number of ways. But it happens to be the case when you draw it, they're kind of not connected. Do you see that now? That there's two pieces to this graph? Well, in any case, this type of graph right here is called disconnected. Okay. And in my next lecture that I'm going to record today and post on YouTube, I'm going to talk about what it means for a graph to be connected versus disconnected. Okay. So please, everyone, stay weary of my YouTube channel because I'm going to start posting quite a lot of videos with relation to graph theory and the optional final project for my 830 class and my mandatory final project for my other classes. Okay. So I hope everyone is doing well, staying safe, and just keep on checking my YouTube channel throughout the week. I'll be posting quite a bit.
Professor, can I have ask you a question?
Yes, of course.
So you said that we have the Python project.
And it's optional for you. The 8:30
So
class, it's optional if you want to take it or not.
so if we do that, is there any more final to do, or it's just that project only
It's just that project part.
for the final?
Oh, no, no, no. So I was going to say that, so originally for this class, Mr. Nguyen said that if you were satisfied with your grade after your second exam, you didn't have to take the final. Is that what I, I think that's what I understand, right?
Yes.
Yes. So if you're satisfied with your grade, you don't have to do the final project. Otherwise, you can do the final project to better your grade.
Okay, I got it now. Thank you.
Okay. Well, I will be in contact with all of you. Email me if you need anything, and y'all stay safe. I will see you next time.